We could actually see it on our instruments almost on the minute, warm air being transported to the site of Oden.
And that was the launching of this domino effect that it then started to melt.
It was a high-risk expedition for two reasons, which turned out to be true, both of them. For one, we didn't know if we were going to make it into the ice at all. And we didn't know, I mean, the basic idea of this expedition was that we would move the ship to wherever the warm air was coming from. The other risk was that we didn't know whether it would be any warm air intrusions at all.
So we went in spring to the Arctic. Usually these expeditions go in the summer, early fall up to the Arctic. But we went quite early in spring to really study the onset of the sea ice melt.
In winter, the Arctic lies shrouded in a blanket of darkness. Due to Earth's tilted axis of rotation, sunlight doesn't reach this frozen expanse until the spring equinox, when the first rays break through, marking the beginning of the Arctic's long summer exposure to the sun. Scientists aboard the icebreaker Oden are here to study the transition from winter to summer and the intricate processes that drive the Arctic's annual melting of sea ice.
Like once we had left Svalbard behind us, it was just flat, and then you start seeing little pieces of ice, and then you get more ice, and then more and more ice, and all of a sudden it almost feels like we hit this like line where there's just ice.
Ship is a very interesting social melting pot. I don't know what you can say. It's a very interesting biotope. It is a confined area for about 80 people for over 6 weeks who live close together. And of course, I would say things are amplified. Conflicts can be amplified, but also positive feelings can be amplified.
The 6-week expedition includes 38 scientists from 10 nations, each specializing in different kinds of scientific measurements.
So the whole concept of the expedition was to look at these warm air inflows and when the melt started. So, and I had this simplistic thinking that melt starts, as you say, when the air temperature goes above zero, which is what I'm used to seeing, if, you know, personally, having experienced a few springs, that's what happens. So when I look back at the results from the expedition, it turns out that this was overly simplified. It's much more complicated than that.
Their mission is to capture what happens as spring arrives, when temperatures finally rise above freezing, studying a vertical range from 500 meters deep in the ocean, through the ice and snow, and all the way up to 15 kilometers into the atmosphere. One key focus is a weather phenomenon known as atmospheric rivers, which has been shown to impact the Arctic at this time of year.
So if you think about a river, then we think about rivers that go on the earth, have a lot of water. If you think that, we put that a bit higher up in the atmosphere. So in the atmosphere, you have also water vapor. But if we have like these narrow bands of really all the water vapor condensed into a narrow filaments, these are basically these atmospheric rivers.
Atmospheric rivers form over the tropics and are driven northward by shifting systems of high and low pressure.
So we have low pressure circulating anti-clockwise and high pressure circulating clockwise. And if these two pressure systems are next to each other, creates like basically a motion like this. And this really drags these narrow bands and gives a pathway for this moist and warm air to actually transfer and travel north.
The plan is to guide Oden to a region where forecasts predict an atmospheric river carrying warm air will arrive, and there the team will set up instruments and build a temporary observation station on the ice.
You have a plan, you have an idea, and then when you start the campaign, reality kicks in, and not everything you want to do happens.
But as the days pass, weather forecasts show no signs of incoming atmospheric rivers. Early in the season, thick ice also complicates navigation, preventing the team from moving as freely as planned.
Captain was a little bit worried that we get stuck in the ice if we forced ourselves to go too far into the really hard and packed ice.
The challenging ice conditions prevent the expedition from reaching as far north as intended, introducing further challenges.
I think what was particularly interesting at this exhibition that we had a lot of polar bear visits, much more than in previous years, because we were quite south, close to the so-called marginal ice zone, where polar bears are much more frequent than further north.
I think on the second day we saw one like really far away. I have pictures through binoculars with my phone that are really bad, but I was like, this might be the only one, so I have to capture it.
So on a typical expedition you would see anywhere from 1 to maybe, if you're lucky, 4 polar bears in a month or a month and a half. On this expedition we had at least 35 visits that we know of. And then there's all the ones that we couldn't see because it was too foggy or they went a path that we couldn't see. Some of these might have been revisits by the same bear. But 35 times we had to sort of do something to manage the situation, which is extraordinary.
Suddenly, a shift in the forecast appears, and the scientists spot signs of an atmospheric river approaching. The team scrambles to set up instruments on the ice.
So we actually built the first ice camp because we knew it's going to come soon.
You're on the ship, and then you stop the ship, but you didn't reach land, and then you get off the ship. You would never do that normally, right? So it was really, it just messed with my head, and you would walk away and you would see the ship really far away, and just that feeling of like we're standing on top of water for just kilometers down. It's really weird, like it messes with your head a little bit.
I remember when I was out on the ice camp, out to our station there, it was quite warm. I didn't need like extra layers. I had too much on me because I was used to minus 15 degrees and suddenly we have 0 degrees. The snow was a bit melting. I could see that. The grains got a bit wetter, snow grains. I thought maybe this is the launching. So now we get the melt onset. But then after this was preceded quite closely with this bigger storm, which then turns the wind northerly, and it was really colder, dry air coming. Temperatures dropped down to -6, maybe -7, which means that the melting didn't start.
The Arctic is warming much faster than the rest of the globe. People say 4 to 5, in certain regions in the Arctic even up to 6 or 7 times faster than the global average.
What happens is that the melt season gets longer, and because of that there's more ice that melts every season and there's more open water.
Open water in the Arctic reflects far less solar energy than ice and snow, which typically send a lot of the sun's rays back to space. The Arctic climate can be thought of as a balance sheet. On one side are warming sources like currents carrying heat northward through the ocean and atmosphere, while on the other are cooling factors like reflected sunlight and outgoing thermoradiation, which is infrared radiation shining from the Earth's surface and escaping into space.
And if these two terms, the plus and the minus, are unequal, if there's more coming in than going out or vice versa, the climate will change.
So climate change manifests most up in the high Arctic, and it's a very vulnerable region, and all the things that happen there are not staying there, they also affect us. We always say what happens in the Arctic doesn't stay in the Arctic. It will also affect us in Europe and the rest of the globe.
What scientists seek to capture are the many small-scale processes affecting this delicate energy balance. Clouds, for instance, play a key role. And for clouds to form, aerosols, tiny particles floating in the air, are essential.
So this is a system we use to measure the size of particles. So we take in the air and then we measure the number of particles, but we only look at one size range at a time.
We're interested in the atmosphere and these little particles in the air that allow cloud droplets to form around them.
To form clouds, you need also particles, and these particles, or aerosol particles, are very scarce in the Arctic. So the concentrations are very, very low. They're sometimes so low that clouds don't even form.
We boiled the water, we put it in this cup, we put a thermometer in it so you can see how hot it was. It was really close to 100 degrees, where you would normally, when you have your cup of tea, it would be steaming, right? But it couldn't because there was such a low abundance of surfaces for the water vapor to condense on. And then we have this little lighter where we, if you kind of roll the wheel of the lighter, you create particles from that. And then you can see how the cloud forms as soon as we add the particles, because this warm, humid air coming out of the cup really wants to condense onto something.
With these experiments, we actually show that what happens if you add additional particles, for example, anthropogenic particles, human-caused particles, then we can also influence the properties of clouds. For example, how white they are, how long they stay in the atmosphere, how they precipitate. And this very basic process understanding on how aerosol particles influence clouds and vice versa, this is something we want to study. And that's particularly important in the Arctic because there are not many natural sources of particles and of course almost no anthropogenic sources of particles.
Hello. Oh, there's a fish. Maybe a... Oh, yeah, funny. Looks like a fish. It's a fish. It's totally a fish.
The free time is really important. Working on a ship can be quite challenging and quite exhausting sometimes. If you do long days out on the ice, it's quite cold. You need some time for yourself.
Every Sunday we have like a special dinner where people dress up.
Nothing really fancy, but just to make a difference, you don't come in your work clothes, right? And there's a 3-course dinner.
The kitchen would prepare it really nice for us, and then we would normally try and take that evening after dinner off.
In the Arctic, spring doesn't unfold gently. When melting begins, it triggers a rapid domino effect. But so far, temperatures remain below freezing and time is slipping away.
We had to be in the harbor by the morning of the 15th, so that was not negotiable.
So we were waiting day and day for this melt to happen. We look at forecast models and they always kept us a bit in the unknown. They were not very conclusive. But then when the models converged to kind of like a better prediction that, okay, on this day it probably will start melting,
And it wasn't until a few days before the expedition stopped that we actually got this, our second atmospheric river, that then came from the south, brought this warmer, moister, really foggy conditions, couldn't go out the whole day.
We could actually see it on our instruments almost on the minute. I think it was 6 o'clock and 10 when we could look at our microwave radiometer, which measures the temperature profile. We could actually see this warm air being transported to the site of Oden, and at a certain point the temperatures were stayed above zero, and that's one definition of when the melt actually started.
I remember chief scientist during our morning meeting, he comes in like, "The melting has started." He was so happy.
The first day of the melt was completely fogged out. No one could work on the ice because the visibility was so poor.
The risk of polar bear attacks keeps scientists from venturing onto the ice in the thick fog. This presents a challenge for the meteorology team, whose measurement station lies a 10 to 15-minute walk out onto the ice. Out there, the instrument's batteries need replacing.
So we were not allowed to go out on the whole day. And of course that was tricky because we wanted to go there first just to change the batteries. That was important. And we thought we're going to lose all the measurements on this day when we actually want the measurements, because now the melt's going to start. It's important. And in this foggy area, we could see maybe just really out of the gangway, just shortly, but we couldn't see none of our instrument, everything were in thick fog. And then we saw polar bear coming out every now and then, and we were like, oh no.
Thick fog blankets the region through the day, and at night the meteorology team takes shifts, preparing to respond if the bridge signals any clearing.
I mean, it was nice because we got finally this atmospheric river with this moisture, and which we actually waited for. So that was great. But is it great if we can't measure it?
They're going to get lost.
Early in the morning, the fog lifts slightly, visibility improves, and a few team members set off.
Then they come back and I meet them on the bridge when they come up, and they tell me that they could see polar bear steps, there's footsteps everywhere around our instruments, but only around. So it kind of just tried to avoid our instruments. We had a lot of cables, everything there on the snow, but it didn't touch anything. Sometimes it was looking up on our radiation instruments, so we can see a peak of a polar bear nose coming up, because a dark surface gives different radiation than like a white surface. So this one we can really clearly see in our data set. That's quite cool. So we measured the polar bear nose. But all the instruments were safe. The batteries didn't die out because of the warmer air. So it lasted a bit longer because it wasn't too cold. So we didn't need too much energy. So that was nice.
And then the forecast said that on the 14th of June, which was the day when we were planning to go back to Svalbard, there would be a major storm in the open water around Svalbard. So we ended leaving already on the 13th. Once we had gotten all the equipment off the ice on the 11th of June, one day after the melt had started, we couldn't go out again on the ice.
So we would have liked to stay. I mean, that's always the case, that the schedule is tight. You have to be at a certain day back in the harbor. There's an exchange of crew, and scientists have booked their flights.
So there were some teams who really wanted to go out on the ice to measure melt bonds, because they occurred within a day from melt onset. It was also raining, so this was really fast. Once the melting started, the melt bonds were there. And that was like kind of the launching of this domino effect, that it then started to melt.
So we were standing on the deck watching the melt ponds forming, but we couldn't sample them because of the weather.
But still, we have gotten a huge amount of data, so I think we can be very happy and proud of this data.
The expedition returns with a wealth of data for analysis.
You have like a year and a half, 2 years of planning, and then you have 6 weeks of expedition, and then you have 3 to 5 years of post-processing of the expedition results.
So now comes all the hard work, now that the fun's over. No, it's actually really fun also to work with the data, because it's so different when you're on the ship. Then we look at it every day. We have these quick looks where you kind of look, okay, what's happened since last time I looked? But now when we're home, we look at it as one whole piece. And then you really start seeing these changes where we can see, oh wait, here something happened. How does that connect with what was happening in the meteorological measurements, or in the people looking at for the people looking in the ice, or the biology that we measure in the ocean, you know? And all these things can link together. So that's kind of what we're working on now.
Okay, it's almost 1 o'clock, and we would like, Paul and I would like very much welcome.
Nearly a year later, the scientists reconvened to compare findings. For example, the Aerosol team reports a discovery.
It was organic.
At a specific moment, the air was suddenly filled with new tiny particles, likely originating from biological activity within the ocean and ice, offering a tantalizing glimpse into the complex Arctic ecosystem.
We didn't think about it at the time even, because we were looking at the data one day at a time. But when you see the whole time series now, it's really evident. And so that was really a big thing for us. So we can see when the summer started for the aerosol particles, and it wasn't when the melt started. It was when we had this transition.
This fog rolled in. So the whole concept of the expedition was to look at these warm air inflows and when the melt started. So, and I had this simplistic thinking that melt starts when the air temperature goes above 0. So that is one of the things that came out of this workshop that we just had, that when melt starts depends on what you're looking at.
And it's a very unique data set that we can use to do all kinds of improvements, weather forecast models, climate models, process understanding. And I think we're very fortunate with this kind of data we have actually gathered there.
So we have braved the risk and came back with unique data. And I think that is the definition of high risk, high reward.